This course looks at automotive control systems, the electronic control unit, input sensors, onboard diagnostics, output actuators, and ECU remapping. The ECU is the electronic control unit, or sometimes called the PCM power control module, or ECM electronic control module. It's the brain, and it does the thinking. It works in a harsh environment and is subjected to temperature variations, electromagnetic fields, and high vibration. First, we look at the sensors, which input information to the ECU. Speed pickups are based on inductive or magnetic speed sensors. When a toothed ferrous wheel moves past the magnetic sensor, it excites a voltage in the pickup coil, producing an electrical analog waveform. The frequency of this waveform is proportional to the speed of the rotation. They are used for crankshaft, camshaft, and wheel speed sensors. The angular position sensor uses a resistor or potentiometer to determine position. As the wiper moves, the resistance is varied and provides a signal to the ECU. They are used for accelerator position and fuel level measurement. Temperature sensors use a thermistor which is sensitive to a change in temperature. It has a negative temperature coefficient. The resistance of the thermistor decreases as temperature rises. They are used for intake air and coolant temperature. When resistance decreases, there is an increase in current, which is converted to a voltage signal for the ECU. The hot wire mass airflow sensor, MAF, measures the flow of air into the engine. When we look inside the housing, we see an electric wire which is heated by an electric current and is maintained at a constant temperature. When the engine is started, current passes through the wire and heats it up. As the wire heats, its resistance increases and it limits current flow. An equilibrium point is reached between the heating effect of the wire and the cooling effect of the moving air. When more air flows over the wire, it is cooled. Resistance decreases, allowing additional current to flow until equilibrium is again achieved. The ECU uses the amount of electric current flowing to the heater to determine the mass of air flowing into the engine. It takes into account the temperature and density of the incoming air, and addition correction factors are not required. The NOx sensor allows the ECU to listen to the engine. It is based on a vibration sensor which consists of a piezoelectric element and is attached to the engine block. The energy from the vibrating cylinder block is converted into an electrical signal for the ECU. When the onset of the combustion knock is detected, the ECU will make appropriate alterations to the timing. The O2 oxygen or lambda sensor measures the amount of oxygen in the exhaust gas compared to the oxygen in the outside air. It generates a voltage from almost 1 volt in rich conditions to near 0 volts in leaner conditions, and the signal is sent to the ECU. The ideal air-fuel ratio occurs near the change from 1 volt to 0. For a petrol engine, the ideal air-fuel ratio is 14.7 to 1 by weight. Sometimes a HECO sensor is used. This includes a heating element which gets the sensor up to working temperature faster. We will now look at the outputs from the ECU. Ignition timing regulates the timing of the spark relative to the top dead center. A signal is fed from the ECU via a relay to the relevant HV coil pack, which is located on top of the spark plug. The coil pack transforms the signal to high voltage for the spark plug. Cylinder deactivation. On some cars it is possible to shut down some of the cylinders when not required, usually when cruising at light load. This is achieved by movable cam which is splined onto the shaft. When the cylinder is not required, the cam for both inlet and exhaust valve is moved away from the cam follower, leaving the valves in a closed position. A further development with the operation of valves is the camless engine. It does not have a camshaft and relies on electrical solenoids activated by the ECU to operate the valves. This allows immense flexibility with the control of timing and lift of both the inlet and exhaust valves. Fuel injection. Injects fuel according to inputs from accelerator, airflow sensor and common rail fuel pressure sensor. Fuel quantity can be varied by altering the length and number of fuel injector pulses. When operating in closed-loop control, fuel injection is determined by the exhaust gas-oxygen sensor. Most cars have separate ECUs for different control systems, with each ECU having inputs and outputs. For example, the anti-lock braking system would have a separate ECU to the engine management ECU. All the information is transmitted between the ECUs using a bus system called a controller area network or CAN system. Each ECU is programmed to accept relevant information if required. Example, road speed might be relevant to a number of control systems. Here we see an engine control system in operation. When the engine is started and still cold, fuel injection is determined from the amount of air flowing into the engine. The engine will have additional fuel and run rich. This is called open loop control. When the engine is up to temperature and cruising, the ECU will use the feedback from the exhaust oxygen sensor to determine optimum fuel injection, thus reducing emissions and fuel consumption. This is called closed loop control. If the lambda probe should fail, the control system will revert to open loop control as there is no feedback from the oxygen sensor. It will alert the driver via the engine management light. Fuel consumption and emissions will be higher, therefore the car should be taken to a garage for repairs. The O.D.B2 standard, Onboard Diagnostics 2, allows code scanners or data loggers to communicate with the ECU. Fault history and fault codes can be downloaded to determine which sensors are not healthy. Caution must be exercised when using a fault scanner, as quite often when there is a faulty reading from a sensor, the source of the problem might be elsewhere in the system. Also, high resistance electrical cable connections can lead to erroneous readings, so check everything and as a last resort change the sensor. Manufacturers program the ECU according to their requirements, and this information is a closely guarded secret. Normally engines are not operated to the limit and the designers allow a comfort zone, allowing for extreme ambient conditions or poor quality fuel. Recently there has been an emphasis on energy efficiency and fuel economy. However, there are tuning companies which specialize in deciphering the program and modifying it usually to produce more power from the engine. This is often referred to as chipped ECU. Here we look at the basic example of an ECU map, graph or lookup table. The input is the accelerator position sensor and the output is throttle position. In the past they were directly linked by the accelerator cable. Now fly-by-wire is used. For this demo both have a range of 0 to 100%. As the accelerator is pressed, we get a corresponding change in throttle position according to the graph. At 60% accelerator position, the throttle position is also 60%. Assume the driver wants a more responsive engine and gets the ECU remapped with new software. Now with the new graph, instead of 60% we have 80% throttle opening. Some expensive cars have the option of switching between different programs stored in the ECU. In this case they are called Sport Mode and an Economy Mode.